Okay, is this visible?
Yes, ma'am.
Yes, ma'am.
Okay. So, a very good afternoon, everyone. I welcome you all for the Strength of Materials lecture series with the code 18CV32. Right?
Yes, sir.
So, to have a brief brush up the concepts which we have learned in the previous session. So, in the previous session, we have covered about simple bending theory, right? About sagging, hogging bending moment, what exactly is neutral axis, about the pure moment, right? So, we have studied about simple bending theory concept, and along with that, we have derived the simple bending equation, right? So, the bending equation, it's one of the important equation if you are studying the flexural strength of a beam. See, flexure in the sense bending. So bending, either you can say it as a bending equation or flexural equation, one and the same, right? So simple bending equation, let me revise that equation once again, and then I'll continue with the next part. So can you tell me, anyone, what was the equation which we have derived yesterday? Yes. Now that equation, you should be acquainted with that equation. Okay. So even when you woke up at night, 2 o'clock, you should be able to say that equation. That's how the equation is important to you now. What is that equation? Simple bending theory equation. M by I is equal to, yes,
E by R.
E by R. Very correct. M by I is equal to E by R is equal to sigma divided by
Sigma by Y, ma'am.
sigma by y. Very correct. So this is
Y.
the bending equation. Yes, fine. Thank you. So this is a bending equation which we have learned in the previous session. So we have also discussed what's the importance of that bending equation. Okay, let me revise that importance of the bending equation once again, and then I'll continue with the next part. So these are the things which we have learned in the previous session. So today, let me revise that bending equation. As you said, it is the equation, final equation is m by I is equal to E by R is equal to F divided by, sorry, sigma divided by Y. So of course, in some of the textbooks, it is F divided by Y. Here I have taken bending stress as sigma. In some of the textbooks, he may take it as bending stress as F. Okay, only the notation is going to change, but overall the flexural equation, bending equation remains same. Either you take F or sigma, it is one and the same, right? So let me revise this. Here, M is basically the applied moment, okay, and I is moment of inertia, E is, capital E is Young's modulus, R is radius of curvature, sigma is the bending stress, and Y is the distance from the neutral axis to the considered layer or considered element, right? So these are the things which we have learned in the previous session. And this equation, I have told you something about the assumptions. So when you say the assumption, this equation holds good for only those members, for those who are only for those members which are homogeneous, isotropic, and uh, it is not, this equation is not valid for a very large beams because there the deflection is maximum. So when the deflection is maximum means R tends to be maximum, right? So that is the limitation of this bending equation. So whatever I have said now, same thing, I have written it here. So always whenever you derive any equation, you should know what is the importance of that. So the importance of this bending equation is, see, suppose if I give you any beam, if I give you a simply supported beam subjected to concentrated load, will you able to find the bending moment? Maximum bending moment. If I give you any beam, are you in the stage of to calculate the maximum bending moment? Yes or no?
Yes, ma'am.
Right. So now at this stage, you are able to calculate the maximum bending moment, right? So please observe this equation. M you can calculate very easily because you know how to calculate the bending moment now. I you can calculate. What is I? Moment of inertia. So in the first year, you have learned how to calculate the moment of inertia. It can be a rectangular section, it can be circular section, or it can be I section. So you know how to calculate moment of inertia. Of course, maybe you have forgotten, but you can revise it, right? But you know what is the procedure, right? So you know how to calculate M, you know how to calculate I. Now that means if M and I is known to you, you can easily calculate the bending stress sigma wherever you want on the beam. Wherever you want on the beam, in the sense, whichever fiber you consider, you are able to calculate the bending stress. So depending on that fiber, you can calculate this Y, because it is a distance from the neutral axis to the considered layer. So M by I is equal to sigma by Y. This plays a very important role to calculate the bending stress wherever you want in a beam. So that's the importance of this equation. Similarly, if Young's modulus is known to you and radius of curvature is known to you, even then you can calculate the further all other values as well. Okay, so this is the importance of this equation, and these assumptions we have already discussed in the previous class. Okay, now based on this equation, of course, let me brush up, or let me revise this part once again, because I feel this is one of the important part to discuss. See, this is a rectangular section beam. Okay, see, a beam can be of any section. A beam can be a rectangular section, I section, or a circular section, right? Any type of beam it can be. So let's take a beam of rectangular section. So I have drawn a rectangle. So I have shown the neutral axis. Okay, for this rectangular beam, I have drawn this stress distribution diagram. Yesterday I have covered this, right? Stress distribution diagram, bending stress distribution. How did I draw this diagram? See, suppose if this is your baseline, okay, we know that a beam, it is subjected to both the types of stress, compression stress as well as tensile stress, depending on sagging and hogging, right? So both the stresses have been shown here. One in the positive direction of X, one in the negative direction of X, depending on tension and compression. So this is the bending stress diagram for a rectangular section. Similarly, I'll show the bending stress variation for I section also. Let me show that. Yes, please observe this. Please observe this. See, this is a rectangular section. Okay. Please observe my cursor. Okay, this is my rectangular section. Okay, so this rectangular section, observe this third diagram, FB max. FB max in the sense, here F in the sense bending stress. This third diagram indicates the bending stress distribution. So you can see at the neutral axis, what is the bending stress? It is 0 here. As and how you move in the top part, as and how you proceed at the top part, okay, the bending stress is increasing. Similarly, as and how you proceed at the bottom part from the neutral axis, similarly, once again, the bending stress is increasing. But it is reversed. Just that is because, just to show tensile and compression, that's all. Okay, so if it is simply supported beam, then you will observe that top part will be compression, bottom tension. Because simply supported beam, apply the load, it will undergo sagging. Okay, so when there is a sagging bending moment means what top will be compression, bottom will be tension. So that compression I have shown it here, bottom tension I have shown it in this way. Okay, so this is the bending stress distribution diagram. So, and once again, you can take any layer. Here you can see I have shown a small dotted lines here. Okay, so for this particular layer, if you want to calculate bending stress, yes, you can calculate bending stress. So just extend this layer here. So I'm just projecting this layer here in the bending stress diagram. I can easily calculate. So FB, now as per your equation, it is sigma B. It is bending stress, right? So FB I can calculate wherever I want, depending on your Y. Y is the distance from the neutral axis, right? So this is the bending stress distribution for a rectangular section. Now let's come to the I section. Let's take this I section. At the bottom you have this I section. So a beam can be I section or rectangular section. It depends. So here I'm taking this I section. Now what is the difference? Only the inertia is going to change. Yes or no? For rectangular section, the inertia is different. For I section, the inertia is different. Agree? Yes or no? Yes? Yes? Agree for this? I section and rectangular section, what is the difference? Can you see the difference here? I section and rectangular section. Can you tell me what is the difference? Am I audible to you?
Yes, ma'am.
Okay. So can you tell me, you can see the two here. One is rectangular section. Can you tell me what is the difference?
Shape.
Okay, not exactly shape. In the first year you have learned, what is, can you tell me what is inertia? Yes? What is that inertia?
Inability to move.
Yes, ability to
Move.
move. Anyone else? It is the resistance offered by any applied load. Yes or no? Is it? It is one of the physical property. It is one of the physical property of a member which resist the applied load, which give you resistance. Yes or no? Right? It is one of the dimensional property. For a rectangular section, if breadth is d and depth is d, can you tell me what is the inertia? Is it bd cube by 12? Yes or no?
Yes, ma'am.
Is this bd? Yes, inertia is basically a dimensional property, physical property. So it is bd cube by 12 for a rectangular section, and you have this I section as well. See, for a rectangular section, I have shown you how is the bending stress variation. This is my bottom. I am showing you I section. Even for I section, and here I am showing you the bending stress variation. Please observe the bending stress variation for both I section as well as rectangular section. Please observe the bending stress for both I section as well as rectangular section. So now just observe this bending stress. Of course, there is no much difference at magnitude, but there is no much difference in the shape. And looking at this, can you tell me which section proves to be economical? Whether it is rectangular section or whether it is I section? Can you tell me which section proves to be economical? Rectangular section or I section? Which is good? Which is economical? Not exactly good. Which proves to be economical?
I section, ma'am.
Can you tell me how? Justify. Can you justify your answer? Yes, you are absolutely correct. It is I section. Can you justify your answer? Go ahead. Even if it is wrong, no worries. Go ahead. Yes? Anyone else? Parvati, you're there?
Can take more.
Yes, Suraj. Yes. See, what I'm telling
It
is,
resists,
yes.
it resists more load, ma'am.
Which I section resist more load?
Yes, ma'am.
See, I'll give you the same section of breadth B and depth D. Even for I section, the top width is same B and entire depth is D, it remains same. Now tell me, just see the bending stress variation. It is almost same. How can you say it is taking more load? Yes, please observe the sections. Rectangular section, I section, bending stress variation is almost same. How it is economical? Megha, Parvati, Shilpa, you're there?
Yes, ma'am.
Yes. No idea?
They have to take load on flange, ma'am, and distribute the foundation.
So what? See, what I'm saying here is, okay, let me explain this. See, you have this, okay, it is not able to select here. Let me show it here itself. Okay, see, basically in this particular, okay, let me show it here. You see, just observe this rectangular section. My cursor is visible to you? Yes?
Yes.
Yes,
Okay.
ma'am.
Okay, fine. See, just observe the first section. This is a rectangular section. For this rectangular section, you have this bending stress variation. Similarly, for this I section, you have this bending stress variation. Okay. Now, why I'm saying that I section is economical because, why I'm saying I section is economical because for the same breadth B and for the same depth D, please observe the area. Okay, please observe the cross-sectional area. Can you tell me where it is maximum, where you have provided the extra material, in the rectangle or in the I section? Yes? Did you get my question?
No, ma'am.
See, this is rectangular section. Okay, let me show it to you in, okay, let me show it here. Okay, now observe this carefully. See, this is basically, this is a rectangular section. Okay, and the entire area is, I'm just doing the shading part. Okay, so this entire area is covered here. But whereas in I section, for the same breadth and for the same depth, okay, this is my I section. For the same breadth and for the same, now this is my I section. Okay, just where did this part go? Is it not I section is economical here? You're providing less material here. Where did
Ma'am,
this portion go?
cursor is not moving, ma'am.
Cursor is not moving. You're not able to see my diagram.
Yes, ma'am.
No, ma'am.
Okay, let me show this once again. Let me share this once again. Now please observe. Is it visible? I'm showing it in paint. Is it visible?
No,
No,
ma'am.
ma'am.
No, ma'am.
Okay.
Previous screen is visible, ma'am. Rectangular and I
Let
section.
me. Okay. Now please check.
No,
It is
ma'am.
still the same.
Yes, ma'am. It is stagnant, ma'am. Your cursor is also not moving.
Okay. Okay, now is this visible?
Yes, ma'am.
Yes, ma'am.
Yes,
Yes,
ma'am.
ma'am.
See,
Yes.
see in the first portion, this is my rectangular section. So what is the area covered here? I have shown you the shaded lines. This is the area covered. Okay. For the same breadth and for the same depth, I am showing you the I section here. Okay. I am showing you the I section. And for both bending stress and for both I section and rectangular section, this is your bending stress diagram. For both, this is the neutral axis and this is your bending stress diagram. Okay, for both rectangular section and for both I section, this is your bending stress diagram. Where did this area go? See, for rectangular section you have the same bending stress variation. For I section you have the same bending stress variation. So there is no point in bending stress variation for I section and rectangular section. What is I am talking about is, I say that I section is economical because, see, when you come to the area or when you come to the point how much material you have provided. See here, the area is maximum in the first rectangular case. But whereas in I section, this material you have already removed, correct? Just compare the area. Where is the area maximum? Whatever the, in I section, whatever the shaded area I have done, this is entirely, it is removed. This part is removed. So which area is maximum? I section or rectangular section?
Rectangle.
Angular section.
Section.
Rectangular section. See, for both the cases, you are getting almost the same pattern of bending stress. So which is economical? That's what I'm speaking now. Now, can you tell me which is economical
I
now?
section.
I section is economical. Are you getting my point?
Yes, ma'am.
For the same cross section, you are getting the same stresses. Then why to go for the rectangular section? You are provided the I section. That's what the meaning is. And that's how you need to give the justification for the economical section. Is that clear to you? Yes?
Ma'am.
Yes,
Okay.
ma'am.
Okay. So this is what I just wanted to concentrate now. So now I'll go to the next part. Okay, now I'll go to the next part. Another thing what you need to learn in this concept is what is moment of resistance or moment carrying capacity. Okay, is this visible to you?
Yes, ma'am.
Okay, let me share this once again. Okay, is the screen stable or it is moving?
Stable, ma'am.
Stable, ma'am.
Stable, ma'am.
Stable, ma'am.
Okay, let me do this once again. Now it is visible.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
See, what I was talking about is about the moment of resistance. See, while deriving the bending equation, you have learned about something known as m dash, right? M dash, that's what the term you have got in the derivation. What is m dash? M dash is basically the moment of resistance given by the structural element or given by the material to your applied load, right? So that moment of resistance m dash, we say that always all the beams or the column or a structural element to be in equilibrium. So for equilibrium, we have taken m is equal to m dash. That means applied moment is equal to moment of resistance. See, let me clear the 2 points now. What is applied moment? What is moment of resistance? Let me clear that to you first. Then I'll come back to this point. Let me clear you one point. Okay, is the paint visible to you? Okay, see,
Yes, ma'am.
I'll take a rectangle, I'll take a cantilever beam. Okay, I will take a cantilever beam subjected to concentrated load at the end. And let's say the length of this beam is L. I'll take a cantilever beam. This is my A point and this is my B point. This is my cantilever beam. Can you tell me what is the moment generated at A? The moment that is generated because of the load P. Can you tell me that moment? What is the moment generated?
PL, ma'am.
P into L. Agree for this? So
PL.
M is, yes, exactly. So M is equal to P into L. What is this M is equal to P into L? M is equal to P into L. It is the applied moment that is generated because of your load. Are you getting my point? This is the moment that is generated because of the load. For this particular moment, the material will also give you some resistance. Yes or no? If someone pushes you, will you give some resistance or no? Because of your inertia. Yes? Always the beam tries to give some inertia. Initially, it will not undergo any deformation. It will give you some resistance. So that resistance is generated at the fixed end. If this moment is now in this moment, what is this moment? Clockwise or anti-clockwise? It
Clockwise, ma'am.
is clockwise moment. So if the clockwise moment is generated here, can you tell me how should be the resistance? Can you tell me what is m dash is equal to? M dash is basically moment of resistance that is generated by the material to your applied load. Can you tell me what is m dash now? M is equal to
My
clockwise moment P. Exactly. Instead of saying minus, I'll say it as anti-clockwise. Am I correct? So moment of
Yes, ma'am.
resistance, very correct. So moment of resistance is basically, it is opposite to the applied moment. Are you getting my point? And we say that all the beams are in equilibrium. That is why we say M is equal to M dash. M is equal to M dash to make sure that the beam is in equilibrium. That means applied moment M is resisted by M dash. That's what the meaning is. This is moment of resistance that is given by the element or the material. And how this is generated? This is generated by the inertia that the beam is having. Inertia is always very important. So now you should understand what is the practical meaning of inertia. So in the first year, you have calculated many more inertia for all the sections, for rectangular section, I section, circular section. Maybe there you have calculated in terms of magnitude. But now you should understand what is the practical meaning of inertia, right? Or you can take a scale. Okay, I hope everyone is having scale. 15, you can take either 15 centimeter scale or 30 centimeter scale. Take a scale and bend it in both the direction. Okay, hold your in one direction first, then try to apply some load, bend it in one direction, and hold it in other direction also, and then try to bend. You can see that at one side it will not take maximum bending at all. That's the reason, because at the cross section it is having maximum inertia, because there the BDQ by 12 magnitude is very high. You can give a try. Okay, give a try, take a scale and try to bend in both the direction. Then you think what is the point there. Okay, so there actually then inertia comes into picture. So what I wanted to stress in this concept is applied moment and moment of inertia. Both are equal, opposite in direction, and for equilibrium we take M is equal to M dash. Okay, now let me come to this point now. Yes, I was talking about moment of resistance. Yes, so usually you get a question like, briefly explain about moment of resistance or moment carrying capacity of the beam. So you may get it for 3 to 4 marks. What is moment of resistance or moment carrying capacity of a section? Or it can be, I also asked in other ways, briefly explain strength of a section. So strength of a section, your strength is nothing but your resistance to the applied load, correct? Strength is nothing but the resistance to the applied load. That is nothing but M dash I'm speaking about, right? So either you may get a question in terms of moment of resistance or moment carrying capacity or strength of the section, one and the same. Okay, so for this, what you should do here is take the bending equation, M by I is equal to sigma by Y. Okay, take this bending stress outside. So what do you get? Sigma is equal to M by I into Y, right? Now, always while designing, okay, always while designing, there you should know something known as maximum stress and permissible stress. You should know something about the maximum stress and the permissible stress. Suppose you have a rectangular beam, and rectangular beam, it can carry maximum load of only 100 kilonewton. Let's say that a beam can carry maximum load of 100 kilonewton. Okay, now that means what is the maximum capacity of the beam? It is 100 kilonewton, correct? Now suppose if you are using that beam in your any building or any construction, okay, then there you should design that beam first. Before constructing, you should design that. Now while designing, you should never take that maximum load. You should never take that ultimate load 100 kilonewton. You should always give some safer limit, or we can say that it is a factor of safety. You have learned what is factor of safety in the first module. So by giving some factor of safety, I'll come across something known as permissible limit. So permissible limit, of course, you can call it as the elastic limit also. Up to elastic limit will give you the range, right? So up to elastic limit, you can always apply the load. Why? Because when you remove the load, it will regain its original shape and size. Beyond elastic limit, if you apply the load, it will not regain its original shape and size because it is a permanent set. A permanent deformation occurs. So that's why you should learn something known as permissible limit. So always while designing, you should make sure that it can be either beam, column, or any structural element. You should not design it for the ultimate limit or the ultimate point or the maximum limit. You should be on safer side and you should design it for the permissible limit. So permissible limit means it is less than your ultimate point. So in my case, as I said, if I take a rectangular beam of 100 kilonewton, you should design it for say around 50 or 60 kilonewton. Are you getting my point? What is the meaning of maximum limit and permissible limit? Is that point clear to you?
Yes, ma'am.
Okay. Now that's why with that case, that is what I have written here. Sigma max. Sigma max in the sense you can call it as ultimate stress or the maximum stress. Sigma max is always less than or equal to sigma permissible. That's what I have written here. The meaning I have explained it now. Sigma max is always less than or equal to sigma permissible. Okay, that means while designing any member, any column, any slab, you should make sure that the maximum stress should be always less than the, maximum stress what a member is subjected to should be always less than the permissible limit or the permissible stress. So now if I take this permissible stress, see what I can write here is by taking this m by I, y max is equal to sigma permissible and m is equal to I divided by y max into sigma permissible. Okay, so please observe this equation. M is equal to I by I into sigma. Here sigma is nothing but permissible stress. Okay, now don't call it as a maximum stress, it is a permissible bending stress. So M is equal to I by Y maximum. Why I maximum? Can you tell me why did I write Y maximum? Because Y can be calculated anywhere in the section. Y is maximum only at the top. Agree? Can you tell me where is the Y maximum? Whether the Y is maximum at the center or at the top. Anybody? Where is the Y maximum? At the center or at the top? Yes? Where is the Y maximum? Shall I show it to you in the diagram once again? Where is the Y maximum? Okay, let me show you that as well. Yes, now let me, okay. Okay, now tell me where is the Y maximum? What is Y basically? Y is the distance from the neutral axis to the considered point. This is your Y. Where is the Y maximum now?
At the
Observe my at the
end.
not at the end. Can I call it as at the surface? Yes or no? Right, very correct. So at the
Yes,
surface, always at the top surface or at the bottom surface, there the stresses are always maximum. Bending stress, always remember this. Bending stress are always maximum at the top surface or at the bottom surface of the beam. Okay, because Y is maximum. Y is maximum at the top surface. That is why the bending stress are always maximum at the top surface or at the bottom surface. Okay, now that is why I have taken Y maximum in my PDF, sorry, in my equation. Okay, so the equation here is M is equal to I divided by Y max into permissible stress. So now I'll assume that I by Y, I'll assume it as Z. Okay, I by Y, I'll assume it as Z. What is Z? Z is called as section modulus. What is section modulus? It is the ratio of inertia divided by distance from the neutral axis to the considered layer. That ratio is called as section modulus Z. So M is equal to Z into permissible bending stress. So this equation you need to remember. M is equal to Z into permissible stress. What is Z? Z is basically, it is a ratio of I divided by Y. What is I? Inertia, moment of inertia. What is Y? It is the distance from the neutral axis to the considered layer. So M is equal to Z into sigma permissible is called section modulus. Okay. This is the section modulus, and let me define this. Section modulus defined as ratio of, as I said now, it is the moment of inertia to the extreme fiber distance. Either you can say it as a fiber or an element, it is left to you. So it is the ratio of moment of inertia to the extreme fiber distance from the neutral axis. Okay, so this is about the moment of resistance. So here basically we started with moment of resistance. To define this moment of resistance, this is how you need to define. Okay, this moment of resistance, it is a product of section modulus into the permissible bending stress. So moment of resistance, it is basically the resistance to the applied load. How much your beam is going to resist for all the applied bending moment. That is the strength of the section. Okay, so if a question is asked to you, this is how up to here you need to derive this. Okay, up to section modulus. Next, before I go into the problems, numerical examples, let me cover few of the formulas. Okay, of course, few formulas you have already learned in the first year. Let me have a brief brush up of that. Okay, so the first formula is, consider a rectangular section of breadth B and depth D here. Okay, breadth B is not given here. Kindly make a correction. Okay, so consider a rectangular section of breadth B and depth D. So this is my neutral axis at the center. Okay, now what is the Y max? Can you tell me what is Y max here? Depth is D. So what is Y? Y maximum. First reply. Depth is D. Can you tell me what is Y max is equal to?
D by 2, ma'am.
D by 2, very correct. So depth is D, Y max is equal to D by 2. Either from top or bottom, it is same, D by 2. Okay. Now, can you tell me what is moment of inertia? I. You know that in the first year you have learned moment of inertia for a rectangular section, I is equal to BD cube by 12 or DB cube by 12, depending on where you are actually applying the load. Correct? So this is BD cube by 12. So BD cube by 12 here. So if you are applying the load in this way, if this is your load, then the parallel to the load, that becomes your D. Please remember this. See, because in sometimes you may take it as BD cube by 12 or DB cube by 12. How to consider this? Just remember this. See, if you are applying the load in this way, the parallel dimension to your applied load becomes D. So which is my parallel dimension to my applied load now? It is D. So BD cube by 12. Suppose if it is reversed, if I'm applying the load in this way, then it is DB cube by 12. Please remember this. Okay. So now in this case, it is BD cube by 12. I is BD cube by 12. Y max, as you said, it is D by 2. So now you should calculate what is section modulus, because section modulus, see, it is one of the important property of a member or any element to show what is the strength. See, if you want to talk about strength of a beam or a strength of a column, then you should find out something known as section modulus. Higher the section modulus, then higher is the strength. Higher the section modulus, higher is the resistance. That's how it indicates. Okay, so always when you are talking about the strength of a beam or a strength of a column, you should find out something known as Z, section modulus. Okay, so it is I divided by Y max, that is BD square by 6. How did I get BD square by 6? Take a ratio I by Y. I is BD cube by 12. Denominator is D by 2. So 2 goes to the numerator. So 2 and 12 will get cancelled. What remains is BD square by 6. So either you remember this procedure or you remember that Z is equal to BD square by 6 for a rectangular section. It is left to you. So however you want, you can remember this. Either you remember this part or you remember Z is equal to BD square by 6. Okay, next. Second formula. Suppose if your rectangular section is hollow. Hollow means you have some gap inside the beam. So as you can see in this picture, this is a hollow rectangular beam. Okay, this is a hollow rectangular beam. So hollow means at the central portion there is no material at all. This is hollow. So what are the dimensions now? Outer dimension is capital B and capital D. Inner dimensions are capital B and small b and small d. These are your dimensions. Now in this case, what will be Y max? Whenever you get hollow section, Y max remains same. It is capital D by 2, not small d by 2. It is capital D by 2. Okay, please remember this. So Y max is capital D by 2. And what is I's inertia for this hollow section? The inertia for this hollow section is 1 divided by 12. that is BD cube by 12, 1 divided by 12, capital BD cube minus small BD cube. Okay. Now, once again, take the ratio I by Y to get the section modulus Z. So the final formula is 1 by 6 capital BD cube minus small BD cube divided by D. So once again, either you remember this Z formula or you remember this I and Y. That's enough, because ultimately you're going to find out the Z value in the numerical examples. So either you can do this I by Y ratio or you can remember this Z. Okay. Next, for a circular section, what about circular section? So this is my circular section. I have drawn the neutral axis. So when you get this circular section, then what about Y? Where is the Y maximum? Once again, it is if circular section, if the diameter is D, then Y maximum will be D by 2. Okay, remember this. So what is the inertia for a circular section? You have learned it in first year, pi by 64 d raised to 4, right? Pi by 64. And the proof of this inertia or the derivation of this inertia, you can check your first year reference books. Okay, so I is pi by 64 d raised to 4. And the Y max for a circular section, it is diameter divided by 2. So it is Y max is equal to D by 2. So take the ratio now. Z is equal to I by Y. It is pi d cube by 32. Correct? So just remember this. After this, I'll go to the numerical examples. Now the last one is hollow circular section. Now you have learned the rectangular section, hollow rectangle, circle. Now the last one is hollow circular section. So I have shown you the diagram of hollow circular section here. Okay. The outward diameter is capital D. Inside diameter is small d. So at the between, you don't have any material. It is completely hollow. Okay. Now in this case, what should be the Y max? It is once again capital D by 2. That is outer diameter divided by 2. And the inertia formula in this case will be pi by 64 d raised to 4 minus capital D raised to 4 minus small d raised to 4. So now once again find out the strength of a section. So or the moment of resistance, Z is equal to I divided by Y max. Okay, so I by Y max is, take the ratio. So you will get pi by 32 d raised to 4 minus small d raised to 4 divided by capital D. So once again, either you remember this formula or you remember the upper part. So you can take the ratio, right? So this is all about the section modulus or the strength of a section for different sections. So I'll be using this in my numerical examples. Okay. So, but what is the importance of this is, if someone asks you if by giving a beam, can you tell me what is the strength? So someone asks you about the strength means you should be in a position to say that strength of a section is nothing but M dash, moment of resistance. Okay. Strength of a section is nothing but M dash, moment of resistance, which is equal to Z into bending stress or the permissible bending stress. So this is the strength of a section. Okay. That's the importance of that formula. Now, another important thing you need to learn is the last concept, theoretical concept of this part. Next, I'll jump to the numerical examples. The last theoretical concept is all about the flexural rigidity. What is flexural rigidity? So flexural rigidity, see, you have come across a word known as EI. How did you come across the word EI? Let me show you that. See, we have the bending equation M by I is equal to E by R is equal to sigma by Y. Okay, now you should be acquainted with this formula, M by I, E by R, sigma by Y. Okay, now in this formula, M by I is equal to E by R. Observe my cursor carefully. I'll take this M outside. Okay, what do you get? It is E into I into 1 by R. E into I into 1 by R. So what is this E into I? This term or this notation, this E into I term itself is called as flexural rigidity. So E into I is flexural rigidity, which is defined as it is the force couple required to bend the structure in 1 unit of curvature. Observe this carefully. It is the force couple required to bend the structure in 1 unit of curvature, right? It is the force couple required in the sense, see, if you take this E into I, if you want to know what is E into I means, you should know how much moment is applied and how much R is applied. Let's say that M is 1 unit and R is also 1 unit. It can be any unit. R, it can be in any unit. M also, it can be in any unit. Let's say it is 1 unit. Okay. So now if you want to define this EI, that is flexural rigidity, then EI, the term EI is, it is the force couple required, or you can say it is the moment required. You can call it as either the moment required or the force couple required. Okay. So it is the moment required to bend the structure in 1 unit of curvature or in 1 unit of radius of curvature. So if this R is 1, so that is termed as E into I. That is flexural rigidity, EI. Okay. So this concept you need to remember. Next, about the pure bending theory, I have already explained to you. Okay, with example I have explained this. So next comes is modulus of rupture or flexural strength. Modulus of rupture or flexural strength. So it is the measure of maximum load carrying capacity or the strength, or it is defined as stress at which the material breaks or ruptures. Okay. So if I give you a beam and if I ask you to calculate what is the flexural strength, flexural strength is basically bending strength. How much it is able to resist the bending. That is called as flexural strength. So to speak in general, how much, if I give you a beam, if you apply the load, how much your beam is going to resist the bending or the deformation, that is termed as flexural strength. So to define this in a technical way, it is a measure of maximum load carrying capacity. So when you test this specimen in universal testing machine, there you need to measure how much it has taken the load. What is the maximum load carrying capacity? So that indicates your flexural strength. Okay. So it is defined as maximum load carrying capacity or the maximum stress which can carry without undergoing breaking or any rupture. Okay. So that is flexural strength. Okay. So this is all about the today's class. In the next class, we shall start with the numerical examples. Okay. See, in the numerical examples, usually how you are going to get is, they'll ask you to calculate the, usually they'll ask you to calculate the moment of resistance. Okay. How do you calculate the moment of resistance? If I give you a beam, you are in the position to calculate the bending moment. First of all, you should know how to calculate bending moment. After calculating bending moment, you should calculate the inertia. Then you should calculate the Z. What is Z? Section modulus. So if all these quantities are known to you, then you can easily calculate the M dash value. Okay, because all the formulas I have told you now. So with these background, we'll continue in the numerical examples in the next class. Okay. So any doubt in today's session? Do you have any doubts or any clarifications? And okay, let me show you another concept before I go. Okay, let me show you this another concept. Okay, please observe this. See, I have told you. Okay, let me show this. Okay, please observe this part. Please observe this part. Okay. Now, this is the beam. This beam, when you apply the load, it has undergone small amount of deformation. So that is sagging. So it has undergone some amount of curvature or sagging, or it has undergone some amount of bending. Okay, in the first diagram. So when the beam has undergone some amount of deformation, suppose if it is a simply supported beam, if it has undergone any sagging moment, then you can see that bottom part will be in tension, top part will be in compression, center is a neutral axis. Same thing I have drawn it in the bending stress variation. Please observe my bending stress variation in the cross section. Observe the cursor here. Bottom is tension, top is compression. This happens if it is a sagging or if it is a simply supported beam. A simply supported beam, obviously it will undergo sagging, right? Now suppose if it is a cantilever beam, just see what happens. Just observe the bottom portion. If it is a cantilever beam, then what is going to happen? Just observe this cantilever beam subjected to concentrated load at the end. Now when you apply the load, definitely you are going to get hogging moment, correct? It hogs, right? Exactly. So you will get hogging bending moment. So when there is hogging bending moment, means top part will be in tension, bottom part will be in compression. So that's what I have shown here. So this is my bending stress variation at the left side. So here you can see that Sorry, there is slight, okay. Please don't observe this portion. Please observe this portion. Let me show. Okay, please observe this diagram now. So this is a cantilever beam. Okay, so when you apply the load, as you said, it is a hogging moment. So that's why top part will be in tension, bottom part will be in compression. Okay, so top is tension, bottom is compression, and the central, there is no bending stress. Stress is 0 at the neutral axis. Okay, so now with this, all these concepts, we'll continue with the numerical examples in the next class. Any doubt in today's class? Any clarifications to be done? Yes? Any clarifications? Parvati, Shilpa, Megha, Shruti?
No, ma'am.
Okay, is this point understood to you?
Yes, ma'am.
Okay, in that case, let me ask you a few of the questions. If you know the answer, you can answer to me directly. Okay? Shall I ask you a few questions now? Now you should be in a position to answer. Shall I? Yes? Shall I ask you a question?
Yes, ma'am.
Okay, let me draw that question here. Is the paint visible to you?
Yes, ma'am.
Yes, ma'am.
Yes. See, basically, I have a rectangular section here. This is my rectangular section. Okay. Now I'll draw the neutral axis. This is my neutral axis. So I'll call it as NA. Tell me, where is the bending stress maximum? At A layer or at B layer? With justification. Where is the bending stress maximum? At A point or at B point?
At B point, ma'am.
Okay, justify. Why it is maximum at B point? Yes, your answer is very correct. It is maximum at the B point. Why it is maximum?
From neutral axis, so Y is maximum towards B, ma'am.
Okay, may I know your name?
Shilpa, ma'am.
Okay, Shilpa, very correct. So as Shilpa said rightly, so when the distance from the neutral axis increases, obviously your bending stress goes on increasing and it will be maximum at the top, right? Okay, so, and where is the bending stress minimum? Where is the bending stress minimum?
A, ma'am.
At point A, ma'am.
Okay, forget of A and B now. In general, in this particular diagram, where is the bending stress minimum?
Ma'am, at the neutral axis point.
At the neutral axis, right? Very correct. So, fine. So, please remember these concepts. So, with all these basics, we'll continue in the numerical examples in the next class. Okay. So, that's all for this today's session. Thank you.
Thank you, ma'am.